It has been, I would say, 3 months since I last posted on LinkedIn regarding my master's thesis presentation, and I posted this slide, the last one of the penultimate ones, which I will explain in detail. But as someone who worked really hard on my master's thesis and had to prepare a proper presentation in a short time frame, I thought that I give a bit more heart and soul and explain it in a very informal, in a casual manner, what my master's thesis topic is about and how it has, in my opinion, far greater influence in hardware regarding the future. So to explain, I gave my master's thesis about it's June, so it was October 2025 when I finally gave my master's thesis and graduated. And and I wanted to explain it in a very informal manner, my slide presentation regarding what I studied, which was a very novel concept, and uh, explain it to you informally as if I'm having coffee or tea with someone and have a casual talk like in a cafeteria or so. So basically, as you can see, I graduated from the University of Trento, coming from Bangladesh. I came to Italy, and it took a long while, but I managed to finish my master's this topic. And the difficulty was regarding this, and I'll not get too much into details regarding this, but more or less, the master's thesis was an extremely novel concept. It was called Federated Learning, Performance Compatibility, Inference Challenges, and Long-Term Plans. This was a title that I came up. And it was my supervisor here, Davide Brunelli, and I was and I graduated with a degree in Mechatronics Engineering. It's kind of unusual that someone who studied Mechatronics Engineering is working on something heavily software related, but this was my centerpiece. My specialization was electronics and robotics, and I'll get further into detail with that. So, what was my thesis about? Let's look at it. So, the context was testing the performance capability of federated learning training code. So, what is federated learning? Well, it is a decentralized version of machine learning ML where instead of transferring raw data to a central server, they are trained on local devices, localized data without compromising data privacy, but still delivering satisfactory performance. The key word of my thesis is, if you will understand soon, is decentralized. So a decentralized version of processing complex code. So federated learning basically was a research concept first propped up in 2015, and it gained more prominence in around 2016 as I read the history behind it. So it's just a decade old, and we're still learning about what it can do. It's basically the same as what you do with processing and machine learning, but as they say, a bit more decentralized. You think of Linux and open source software like social media like Mastodon. It's basically a more open source version, decentralized version of other prominent social media platforms like uh, Twitter and Instagram and Facebook, something like that. That's what I mean by decentralization. So, what was the main problem statement regarding my thesis? Well, it was the demonstration of training a hybrid model system or training a varied dataset format, training varied dataset format. So, and the solution that I said is a hybrid training code developed to train pre-trained models into one fusion model with performance exceeding its predecessors. Okay, what does this mean? Well, the problem that the thesis had was we were studying embedded systems. We had a project on that course, and that my thesis was centered after doing that embedded systems course project, and it was basically they had a training code. I'll also detail further. They had a training code which uses Python, and it was run on Ubuntu, but the dataset and inferencing of the code needs to be passed on a certain development hardware, and they were all designed for proprietary software, using a proprietary software. So the training code was the only thing that was open source, and that was the core element of my thesis. But the embedded systems laboratory from our university that they provided, I felt it was too much lacking, and I'll get into further details on that. But it took me years to understand that there was a lacking of being able to train hybrid models. It was training more specific training codes, and I wanted to develop a training model that can expand further, add more functional capabilities than what was limited within the lab tested training code. So this slide shows us the training limitations behind what I experienced. I mean, it was only my thesis basically. That the laboratory used certain pieces of hardware, certain pieces of software, and they even had their own sensor tile box. Yes, I remember this was in 2022 when I started out. This was in 2022 with my embedded systems course, and then further down the line with the project as well as starting out my thesis, we were facing numerous functional issues. It was too much closed proprietary software felt, and I wanted it more open source so there can be more areas to develop without fail. So for example, we had problems with dataset creation. We can't unreliable devices like the sensor tile box. Sensor tile box was a smaller version of the STM32 Nucleo board family that we were using, and I even mentioned it in the thesis that it worked for the first time and then suddenly it doesn't work for the second or third time. It just suddenly popped up with data. And there were training drawbacks thwarting FL Federated Learning performance, meaning like I upload a certain piece of my dataset to be trained on the laboratory's provided Python training code on Ubuntu, and suddenly it wasn't working. Like it was showing batch error and everything, if I can remember. And that was frustrating for me, that every time I tried to create a data set and upload, and it wasn't working. And the lab reference is not expansive for random approaches. That was a summary of at the end of my thesis, basically, that at the beginning mainly that I observed that the laboratory materials they provided were not providing sufficient input or allowing sufficient input for us to develop further on it. It was very closed. So what was the thesis mainly about? The inferencing was around pattern design recognition, grabbing hold of a module and then using the motion sensing data to draw patterns in thin air. The computer will read the accelerometer data and guess what I am writing, say a letter or a number, something like that. So that was the mode of inference we were using, and what the aim was to improve the computer and the machine learning training code's ability, as well as the device ability, to tell or guess what I am trying to interpret to it. That's basically what I'm trying to explain here. So what was the contribution from the lab versus what I did? This was the lab contribution. This is my contribution. The lab method was a very conventional approach. It was basically create a data set, train and generate a model file, analyze and validate the model file, and then inference. The hybrid model, the unconventional approach, as I said it, I said unconventional, is that it's a nonlinear model. It works with nonlinear models. It will use the activation function codes SMODE, stratify, and atom, and it will also have a feature called concatenation. Keep this word in mind. This is what I actually posted on my LinkedIn 3 months ago, because this is a very, very unraveling feature that you need to keep in mind. I'll explain what that means. So how was it done in general? Basically, we use the data set to create. Okay, I'll get into it in the next few slides. So create a dataset train model. my approach was create two different types of data sets for data set acquisition, and network that both of them are trained on the network model separately, then infuse them both into a hybrid model, and then you transfer it for validation and inference at once. That was the difference from what my university lab was doing. I wanted to, this is what I mean by being unconventional. So what was the designated hardware that I switched for? The implementation here was basically, this was the hardware, this was the software. This is the STM32 Nucleo board F401RE, the main development board, and on top of it is the X Nucleo IKS0182 motion sensing shield. It's an extension board on top of the main development board. This motion sensing board had accelerometer and gyroscope data. It was basically collecting accelerometer data, X, Y, Z, and I connected it to my laptop and used it to generate data sets. USB cable laptop. Okay, the software here that was used for this hardware is the STM32CubeMX with an Xcube AI tool. So this is the software that was used to generate the code, and an extension tool library was being installed. It was the Xcube AI tool. This was, I think, in version 5.6 or 6.2. I mean, multiple versions had compatibility issues. It's something I even mentioned at the end. The AC6 system workbench, STM32Cube programmer, formatting the board for error connections. Yes, this is another thing. This board faced so many errors, unwanted errors. It was not a smooth sail, and it was very difficult to reset until I learned from my embedded systems project. You can use this software to reset the error connections that I faced when trying to, let's say, upload a code or provide it for inferencing. And the Visual Studio Code software was used for the Python training code, for creating the Python training code. So basically, I went from not relying upon the virtual lab image, virtual operating system the lab provided from Ubuntu. They gave me this, and it was constantly showing errors and constantly logging back and forth on my main Windows hardware. Wasn't feasible. I wanted it to be on one linear platform, so I'm like, no, forget it. I'll go switch to Visual Studio Code, and I'll write the Python code here. I identified that the training code was the Python code, was written in Python, so I wanted to just bring it in the main Windows platform instead, so that it's more efficient to develop and test on board instead of constantly jumping between virtual and main desktop operating system. So these are the tools we had. This was the methodology we switched to. The STM32 board came into the foray of discussion because it was more reliable, and we switched to this even during my embedded systems course project with my teammates, because the sensor tile box just kept crashing every single time. Like this board, it kept on crashing. It even showed this fairly. It doesn't flash. It was too limited. It needed very dedicated software, and it was not open source. I get it was small. Its feature was that it was small, compatible, and fast. You can see this image that it worked back in 2022, but when it went into more reliable performance operations, it just crashed. So I even decided that we're switching to the STM32 board. Then what's the next topic? The implementation. So this is the breakdown of the whole software perspective. We are doing a pattern recognition of vowels, A, E, I, O, U, as samples for the data set. So basically, I grab the board with my hand, I upload the code, I grab the board with my hand, I upload firstly the data acquisition code with my hand, and grab hold of it, swing it around in free air, writing A or O like this, or I or O, and create data points, which is recorded in a notepad file, and that notepad file is then saved in the MOBA Xterm data suite, MOBA Xterm serial monitor, and that data set is later used for training. So there's a data acquisition code and an inferencing code. I'll explain what codes are there. So the inferencing for this experiment is like developing, creating motion letters, creating motion pattern data as if you're writing letters in thin air with the board, and that's the samples for the data set. Okay, so what is the implementation here? Create a data set, train it in the Python training code, then analyze and validate the model, and then pass it on to inference and see if it can read the data. The aim was create a dataset acquisition code, upload it to the board, train it in Python, analyze and validate the model using the CubeMX AI tool, and then use the inference code. So the inference code reads the process of whether the dataset code which is validated is readable, and then whether it can be uploaded to the STM32 board using CubeMX. The dataset acquisition, there are three codes here, three types of code files. Let me explain what these are. The dataset acquisition code, the inferencing code, yes, these two code files are written in C on the CubeMX software. So it directs you to the STM32 CubeMX software that I showed you earlier, CubeMX IDE, the development code software, which is written in C, and these codes will only be these codes will only be bypassed to the STM32 board. These codes can only be uploaded via this software, the CubeMX. This is the only software that will allow codes or C code embedded programming, C language codes uploaded here, basically, including its AI tool. So the AI tool that is incorporated here, which basically says, yes, you can validate this. Yes, I validate this. The software it tells the AI tool tells the software, yes, it's validated, it works, it gives these many outputs. You can then now upload it for interfacing. That's what it is. The Python training code, the model training code, and the centerpiece of my thesis, which is based around federated learning later on, which is centered on federated learning. This is the separate one. This one is not related with the CubeMX, and it's what we use to train our code. So these three and its tool are all around C programming language, and the AI tool has an activation function code, and the Python training code is just like a separate code entity on its own. I hope I was able to explain this a lot easier as a breakdown. I know it sounds very complicated, but I hope this part was easier to understand, because it's very complicated if not broken down into layers. But bottom line is, this board will only accept a very specific type of C coding file from here. What is the next point? Okay, so the laboratory that I was provided as a sample to improve on, it was called dense.py, and it was uploaded here on the their Ubuntu virtual machine. This is the dense.py laboratory training model. It was written on Python. It's a training code that had Keras, which is a high-level API. API means application programming interface for TensorFlow. If you can look it up, it's an important training algorithm. TensorFlow is like the go-to training algorithm in Python, and it is used in the Xcube AI tool extension that you saw on CubeMX I mentioned earlier. And yes, it creates a DNN, dense neural network, and this is its model architecture. You can pause and read what is here, but mainly it has an activation function called ReLU, that's rectified linear unit, which is like the standard for introducing non-linearity. When you have a non-linear programming model, this is what they use. And basically, while my function also had ReLU, it also did something different. And right now we're talking about what the laboratory had versus what I had. I will like expand. I'll proceed further with the next slide of the code. This is where we read our input and output data results. Like all up till this is a serial monitor. It's the mobile extreme serial monitor, and here it shows what is the board reading. So when I upload a code and want to test something, is it reading, is it collecting the letters, the data points of the letters properly, is it giving a reading? This is the serial monitor software that shows it. So I upload a code for data acquisition. I input a letter according to how it's provided, and it creates a string of motion every time I swing the board connected to the USB cable, and these are the readings that come out. So to just understand what this means, this is on the left. That's you see the number of data points being created, and here this is not 0, this is O, and then that's X, Y, and Z data points from the accelerometer data, the sensitivity of the accelerometer data. And this is how I collect it for each and every single letter and create all the data points. I think this was the data acquisition code where I create the data set so it can later learn and train and memorize, and then it can analyze and validate, basically absorb the knowledge, and then it can implement later on. That's what this is about. But I would say that there were a lot of technical issues with regard to this. It was sometimes not reliable, but that's part and parcel of doing research. The accelerometer data, I would say, gave a fair insight into what the board was reading. And this is how I read. I think for every letter I read, different numbers of data sets. I read about 60 data sets, 60 times per letter of the English alphabet, like A, E, I, O, U. For each and every letter I read about 60 data sets and just uploaded. Could have had a bigger sampling size, but I wanted to see how it did with a smaller sampling size as well. So this was the performance output of the dense.py. So as you can see, the lab data set, it was showing basically extremely perfect. You will see that it had 300 data samples, it had a 0.00 loss and an accuracy of 100%. The best result when we look for from our data sets, basically it shows minimal loss and a higher accuracy. And from the graph you can see that you can see the readings that from the 7th, 8th, and 9th and 10th data set you get different readings, and that's because my data set readings from 1st to 6th just didn't work. For some reason it was not validating via the model, and I was a bit frustrated with that. Is it recording? Okay, it's still recording. So basically it was like I had reliability issues with this, and anyway, I chose from the 7 dataset because that's when the validation worked and the inferencing worked. So you can see here I collected 100 samples, 301 loss of 301.34 and 45% accuracy. Then when you should raise the number of samples to 304, the loss decreases and the accuracy increases 75%. Then you create the 9 dataset, 350 samples, and the loss suddenly, the loss decreased, but the accuracy again decreases 10%. Then the 10th dataset, again about 100 samples, but suddenly it shows a much different loss and lower accuracy, lower loss but also lower accuracy. This is unusual. It wasn't predictable, or it wasn't understandable as to why it was swinging. You can see some improvements and whatnot. Up until now, still slide 9 of 15, or slide 10 in this software, that I've talked about what the laboratory files do. Basically, most of the equipment most of the approach that I do, this function code is belonging to the laboratory file. So what did I do? I kept the dataset, the AI tool, and the inference all the same, and decided not to do any major modifications on these because the CubeMX only allows you to bypass on the code or bypass your sets of code with regards to this, and realize that this training code is the only part that I can work on and implement federated learning at a very high influence here. This was the only area where it was more flexible to work with, and so that's what I focused on. Yes, I had to work with certain AI extension and everything, but I definitely worked it with this AI tool is not the generative AI tool. It was the CubeMX AI tool. It was extremely dedicated with respect to the software it had. We're talking about 2022, before like generative AI came to the foray in mainstream social life. This is the CubeMX AI tool from that particular software, and I wanted to develop my own, which can like at least bypass the AI, or at least shows better results than the one AI tool that's here. So where was I? I was okay. So now I'm at slide number 11. Oh, it's slide 10 of 15. I'm excluding the cover page basically. Custom federated learning model trainers. I created my own. I basically made the decision that I do not want to use the lab training code from on Ubuntu. I stick to Visual Studio Code, and this is my approach. I created a single dataset training code for this under this file name. It was called the fl underscore stm32 underscore adj.py, and a hybrid fusion model training code, which is called I named fl underscore fuser.py. So this training code basically it trains and perfects the training code and from the dataset that I created, and generates a model file. It's called a .h5 model file. It's basically a notepad or a text-like file which only the computer and the AI can read. It's not human readable, but it's a file. It's a notepad type model file with a .h5 file extension. And basically that's what the training codes did in general, but I created mine. This one is for a single dataset, and after creating 2 or more model files from this dataset, they were fused into this model code that I created. So I created 2 separate types of model trainers, one for a single dataset and one for fusing 2 dataset or 2 models, pre-trained models, into one hybrid model and generate a super model, which I called it the hybrid model. And yes, they were all in .h5 file format. So what was the comparative analysis? This is the comparative analysis of the model trainer. What made my model training code better than the one from the lab? It had SMOTE, synthetic minority oversampling technique. It tackled training bias. It had a dropout layer in case of overfitting. There's an issue with regards to how much layers of readability you can tell the AI to do. So this dropout layer was in my training code. The laboratory training code dense.py did not have it. And it's also to cut out noise data. There were a lot of unnecessary noise data in the lab training code. Using the Adam optimizer versus the lab using the RMS prop optimizer, and that's because Adam, as you can see, it converges faster. 50 epoch batch size and 50 epochs and a batch size of 32 versus 10 epochs and a batch size of 5. Basically, the dense.py file relied 10 epochs basically mean the number of times it needs to memorize, I guess. The training model needs to memorize so as to process and generate the data file. And I increased it to 50 epochs and a batch size of 32. This was the flexibility. Like every time you fiddled with this code, it only showed error because it needed to rely upon a very specific type of function. But my code, I can flex. I had a lot more flexibility. I can increase. I can even go more than 50, like 50, 100, 150, give a bigger batch size and have better convergence without any technical issues. So more epochs, lower loss, better conversion, large batch, and even faster processing. And another thing was data splitting. That's for using the stratify function. It had this function code on my. It had this function on my code. Train underscore test underscore split. Train test split. This is for balancing class. Whereas the laboratory code, they use manual array shifting. So you stratify ensures true distribution file classes in the original dataset. You can see from my research, extensive research, I've added more function keywords than the laboratory file had, and it made a marked further improvement in the reading and the processing of training the code. So this is the performance output of my trained code versus the one that the university laboratory had. Look at this. I used the same dataset codes that I had earlier, that was generated with the STM32 board. Look at the losses here at the hundreds, and here the losses are 2.64, 2.39 to 1.52. The accuracy, okay, it's also, it may not be satisfied. It reduced. It's like 30% or 40% around that. Look at the loss reduction. It's an average of 97.33%. My train code beat the one that the laboratory file had. It had a massive reduction of loss, but we have a very sad ending to this. I will explain what that is, because ignore the accuracy, because what will happen in the end is what you read about in my LinkedIn post from 3 months ago. Where was I? The model training code. The performance output was this. Okay, you saw the loss. Now here's the performance output with the flfuser.py. So now I compare my single dataset training code to my fusing model training code. And look at this. When I combine the 8 and 9 dataset and create a fusion model, its loss is even lower than the single dataset, 1.54. And yet the accuracy is look at this, 1.5, 1.5, 1.57. The accuracy remains around the 30% mark. So it's still standard, even if it's fused. Yes, the accuracy was expected to reduce, but look at the loss. The loss reduced. Technically, the loss was supposed to increase again when you fuse two model datasets. But my fusion model training dataset reduced the loss. Yes, it used 100 epochs with a batch size of 32. It needed to have more time because it's running pre-trained models and not from a dataset. So going back to my custom model trainers, this one was training the datasets that I created from the CubeMX, and this second training model, the hybrid fusion model that I showed you right now, this one was basically training pre-trained models. The two models that I generated earlier, those two are being fused to create a hybrid model. So I combined this model that I had, it was a combination of the 8th and 9th dataset. This model I had, it was a combination model file, it was a combination of 9th and 10th dataset. And then a third model I created was a combination of the 8th and 10th dataset. Look at the losses. Look at the losses. And the accuracy, okay, 30%, fine. We can improve on that, but the loss was reduced drastically. Now we come to the final slide. Will it work? No, it didn't. This is what I posted, the lack of concatenation. So what does concatenation mean? The my hybrid fuser model had the layers.concatenate function, basically to merge two pre-trained models, and it generated the hybrid model. But the AI tool in XCubeMX did not have this feature, as it showed an error called index out of error. Reason is this AI tool cannot read concatenate layers, hence no validation, no inference, despite better performance outputs. The software CubeMX, the AI extension tool library that was in this software, was showing this error, index out of range. It came here. This was not an issue from my side. It was an issue from the software. The AI tool lacked concatenation. And because it didn't have concatenation, even though my model training model had, I could not test anything. I could not bypass this stage, the analyzing and validation stage, this stage, because of a proprietary software, because of a proprietary built-in tool. And I don't know whether future versions had made improvements on this. Maybe it has concatenation, but it wasn't open to the type of concatenation I had. So that's why I couldn't test its accuracy nor its performance. And that was the conclusion of my thesis. So what was the conclusion? Concatenation in future software versions, that's what's required. Development in fusion models for increasing accuracy. Model compatibility issues addressing. Okay, and with that, I said thank you and asked the panel any questions. So, what was the conclusion of my thesis basically? Basically, in short, I created a better training model, and the proprietary software for my hardware was not validating it because it didn't have the feature. So that's why I couldn't test the full potential of the federated learning training algorithm. You can see that at the stage of when it's being tested and compared to its predecessor, it worked. But then you have the issue of again proprietary software not improving further on what needs to be done. The flexibility to me, the lack of flexibility for testing such functions was a barrier for improvement. And that's the technical issues that we faced. Again, it's the same issue back in my sensor tile box. The sensor tile box just wasn't reliable, as I said before. It was also requiring very specific type of network training. It wasn't open to other types of network training. Those were the other barriers we were facing. But anyway, this is the summary of my thesis. I will further explain what other aspects elements I did. It's a very long video I have explained, but hopefully you find this thesis topic and everything interesting. And if you want research of my thesis document, I think I can share it with you if you can request as a, on LinkedIn as a whole. I hope I hope you find this informal explanation interesting. More importantly, you can leave a like or comment what can be done, and you can reach out to me as a whole if you have any further questions. Anyway, thank you very much, and have a nice day.